So today I thought we'd do another clearing the obstacle type problem. And on the board I've drawn a regular hexagon of side length L with one of its sides flat against a horizontal surface. And our goal is to figure out a couple things about the trajectory that just barely clears this object. In other words, these four upper vertices of the hexagon are going to be just intersecting the trajectory of the parabola. And we want to know what is the range on the table. In other words, what is this distance from launch point to ending point? We want to know what launch angle achieves this trajectory, and also what speed is required to do that. So most of this is going to involve using a little bit of geometry. So remember that a regular hexagon can be broken down into 6 equilateral triangles. Each of those equilateral triangles will have length equal to the length side of the hexagon, which I'll call L. And so what we might want to know are, what are the vertices, the coordinates of 2 of these vertices? By symmetry, we only need really 2 of them. So let's work right here. Let's call these 2 vertices, say A and B. Pretty clearly from the geometry, we know that since this y-axis, which I'm drawing through the symmetry axis, splits this hexagon in half, the x-coordinate here will just be L over 2. The y-coordinate, on the other hand, we're going to have to work out from a tiny bit of trig or a little bit of geometry. We'll come back to it. Down here, the x-coordinate's the one that's going to require a little bit of, or actually, no, the x-coordinate is quite easy here because remember, each of these are equilateral triangles. So if this length is L, this length is also L. And the y-coordinate, again, is going to be something that we have to work out. But it shouldn't be too hard to see that the y-coordinate of point B is really just going to be the altitude of one of these equilateral triangles. And it's pretty quick to see that that's going to be L root 3 over 2. If you want to, you could also say, oh, it's something like a sine of 60 degrees, 60 being the angle of their equilateral triangles. And so the sine of 60 is root 3 over 2. And then everything is scaled by L. Pretty clearly, the y-coordinate of point A is just going to be double that, again, kind of by symmetry. So we'll have L root 3 for the coordinate in the y direction of point A. Now that we know what those are, we can start filling in the details of our parabola that is enclosing this hexagon. So again, by symmetry, I'm not going to go back to the trajectory equation. Let's just do this from scratch geometrically. From symmetry, we know that our parabola is going to take this form. There'll be some downward facing parabola, so I put the negative in by hand. The A will now be a positive number. There's a B term, which is really just going to be the vertex, the y-coordinate of the vertex of this parabola. And notice there's no linear term. And that's because I've chosen my coordinates so that this parabola respects that evenness in its symmetry. So now all we have to do is figure out what these 2 coefficients are, and much of the rest will just come from that naturally. Okay, so let's actually just go ahead and plug in the coordinates of these 2 points, and we'll get 2 equations with conditions on this A and B. So let's start with point A here, the top one. We know that L root 3 is the y-coordinate, and L over 2 is the x-coordinate. So there's our first equation. And we also have this lower equation, which tells us that L root 3 over 2 goes with the y-coordinate, or sorry, the x-coordinate of L. And now it's pretty easy to see that we can just subtract these 2 equations to figure out what A is, for example. The B term will cancel off pretty nicely, and we can combine them. So let's see, what order do I want to do this in? Let's do, say, the top one minus the bottom one. So on the left-hand side, when I subtract these, I'll get L root 3 minus L root 3 over 2, which is L root 3 over 2. On the right-hand side, like I said, the b's cancel out, and I'll be left with 1/4 negative AL squared minus negative AL squared. Watch out for the double negative there. That's going to end up giving us basically 1 minus 1/4, which is 3/4 AL squared. And from this, we can very quickly write down what A is. An L will cancel on either side. And then we can also cancel a 2 on either side. When I go solve for A, I'll end up with a √3/3, which we can leave like that. And I'll have 2 √3/3 L in the denominator. So that's my value for A. We can check that this makes sense dimensionally. Notice that since A is 1 over a length, and I plug that in here, multiply that by a length squared, we do get a length. So everything does check out. That's nice. Once I have A, I can go back to either of these and find out what B is. So let's do that real quick. Let's just plug it into this bottom one here. So we have L √3/2 is minus 2 √3/3L, L squared plus B. And sure enough, if we want to go solve for B, we just subtract things over. One of these L's cancels. So when I move that back over, I'll have 1/2 L √3 plus 2/3 L √3. And 1/2 plus 2/3 is 7/6. So we'll have 7/6 L √3 for our B. So now that we have our A and we have our B, we know what this parabola is, and we can move on to calculating these other quantities. Okay, so now we have our trajectory equation in terms of this L, the length of the hexagon side. Now we just have to extract a little bit more geometric information from it, including some physics. So let's start by figuring out what is the range of this projectile on the table. Well, notice that's just going to be the distance between these two intercepts. To find the intercepts, I can set y equal to 0. Notice that when I move things over, I can drop the negatives on both sides. And now we get some nice simplifications. The √3s do cancel on both sides. I will cancel a 3 on both sides. And then when I multiply things over, I'll get x squared is, what, 7/4 L squared. Now when I take the square root of this, of course, I'm going to end up with a plus or a minus. There are actually 2 roots. So x, these intercepts, are going to be plus or minus √7/2 L, which means that the actual distance between these, the range, is just, well, the difference between these, which will be √7 times the length of the hexagon. So that's the range of this projectile on the table. Okay, let's move on to the launch angle. Okay, to find the launch angle, we're going to want to look at the slope of our trajectory at the launch point and recognize that the tangent of this angle will equal the slope at any point, but in particular at the launch point. So let's compute the tangent. In other words, the derivative of this trajectory with respect to x. The constant term will go away. This 2 will make this into a 4. And we want to know, what is this value at the launch point? Well, we already figured out what the x value of the launch point is. And if we're using the launch point on the left, I want to use the negative. Remember, we said that that was √7/2 L. And so we can clean this up a little bit. Of course, the L's better cancel out. We've got a 2 left over here. And the negatives cancel, giving us that the launch angle must be the arctangent of, what do we have, √21. There's a 2 and a 3. 2 √21/3. If you want to have a numerical value there, I got about 71.88 degrees, if you're interested. So that must be the launch angle, and even though this is a rough sketch, it does kind of look like it'll be a fairly steep launch angle, so I'm not surprised that it's above 70 degrees. Okay, got our launch angle. Now let's finish this off. Okay, to finish this off, let's actually switch to some physics. You could either use conservation of energy, or more specifically, I think I'm going to use vertical kinematics. So we have our constant acceleration, which means that I can write down the velocity in the y direction squared using our time-independent constant acceleration kinematics equation. The Vy here means the velocity in the y direction, and I'm just going to compare what's going on initially to what's going on at the vertex of this parabola. So at the vertex, we know that the vertical velocity is 0. The initial velocity is just going to be v naught sine of the launch angle, and don't forget that's going to be squared. And the acceleration, of course, is negative g. I just need to know, what is this height? Well, that height is exactly this extra constant term in our trajectory equation. So I'll just plug that in right away. Now we do know the launch angle. Technically, we know the tangent of the launch angle, so we're going to need to find the sine of that angle. Let's do that off to the side over here for a sec. So there's a very neat trick that can be done when you don't really care about the numerical value of an angle itself, although we did find that, and I want to keep things perfectly, well, exact. We found that the tangent of this angle was, what was it? Was 2 root 21 over 3, and I want to find the sine of this angle. Well, we know that tangent is sine over cosine, and we know that cosine is 1 minus sine squared. So we can always rewrite things in terms of tangent. In fact, though, another clever trick is to recognize that we could always just draw a little triangle here. Here's my angle theta. I'm not really drawing it to scale. And I want to interpret this tangent as kind of an opposite over adjacent. I'm not really thinking about any triangles from the physical diagram. I'm making up a new triangle. It's a ratio, right? So we could write this as opposite, which is 2 root 21, over adjacent, which is 3. Now, if this is a right triangle, as I've drawn it, we know what the hypotenuse of this has to be. It's got to be the square root of 3 squared, it's 9, plus 2 root 21 squared. Well, that's going to be 4 times 21. And if that's the case, then the sine of this angle, which is what's going to show up in our projectile motion, better be opposite over adjacent, good old-fashioned SOHCAHTOA. So the opposite side is 2 root 21, and this adjacent side, let's see, that's going to be 84 plus 9 is 93. So sine theta is 2 root 21 over 93. It's a little ugly, but such is life sometimes. And now we can go try to simplify this out and solve for v naught. I'll go ahead and cancel this down to a 3. Notice that v naught, well, squared, is going to be a GL, just to get the dimensions right here, and then some stuff. What do we have? 7 root 3 over 3, all over sine squared. This thing squared. Okay, I actually am also realizing this should have had a square root under it. My bad. Okay, now we're going to simplify this as much as we possibly can. Oh boy, okay, so we've got our GL. We've got a 7 root 3 over 3. The 93 square root squared will come to the top as a 93, which I'll want to factor a bit. And then we've got a 4 down here and a 21 down here. Okay, now let's see what we can do. 93 is definitely divisible by 3, giving us a 31. 7 and 21 partially cancel down to another 3. And 31's a prime. So I think that's all we got. We've got GL times 31 root 3 over 12. That's V naught squared, which means that V naught itself is root GL 31 root 3 over 12. And there's probably 1,000 other ways of writing that, but that must be our initial launch speed. Okay, so I think we have everything we need. We've solved the problem of clearing the hexagon. We found the range, the launch angle, and the launch speed, QED.